So today I'm joined in our Bristol studio by astrophysicist Geraint Lewis from the University of Sydney. Geraint, thanks very much for coming in and joining us.
Thank you.
Especially because you're just off a 17-hour flight from Sydney, aren't you? Because you're based over there, although you're originally UK, you're based in Sydney now.
Yeah, I'm originally Welsh. I'm based at the University of Sydney. I've been there for 20 years. And this was the first time I've done the Sydney to Perth and then Perth straight through to London, which is 17 hours. And it wasn't too bad. I saw a few films.
Do you think does the jet lag make it easier or more difficult to comprehend astrophysics?
Look, being an astronomer, you're often just jet lagged from, sometimes you have to spend nights at the telescope. You just get used to it. Power on through. That's what we do.
The reason we're talking today is because you and your colleagues have recently released a really interesting paper basically about the Andromeda Galaxy's cannibalistic past.
Yes. So this is something we had published in Nature last week. And actually, this is something that we've been working on for roughly 20 years now, is to try and understand the feed-in habits of large galaxies. Because what we understand is that even galaxies like our own Milky Way, which are currently a few 100 billion stars, have grown over time. And they grow by basically this process of galactic cannibalism. Small galaxies get a little bit too close, and then the gravity of the big galaxy tears the small galaxies apart, and their stars are added to the big galaxy. So what we want to know is just what kind of feed-in have these big galaxies been doing? Are they like little snack feeders a little bit and very often? Or are they binge eaters? And what we saw with our results last week, it looks like Andromeda went through two big stages of binge eating. One relatively recent in the last 3 billion years or so, and one much older, probably 7 to 10 billion years.
I think, as interesting as all this is, I think most people would kind of say, but how could you possibly know? What sort of observations were you guys carrying out in order to discover this?
So as I said, this is a long-term program. So we have two sort of attacks to solve the problem. Firstly, we wanted to image the outer regions of Andromeda. So anyone who's observed Andromeda, you can see Andromeda with your naked eye if you know where you're looking. And we know that the actual optical disk of Andromeda is several times bigger than the full moon. But we wanted to sort of image the halo of Andromeda. So this large, tenuous sort of region beyond the stellar disk. So it covers a huge swathe of sky, and we wanted to observe it very deeply because we wanted to find individual stars. So we had a very large mapping program with the Canada, France, Hawaii telescope that allowed us to capture large bits of sky in very fine detail. So we could pick out individual stars in the halo of Andromeda. They're giant stars, so they're very bright, but they're very faint in terms of the observations. And so the first thing that revealed is essentially all this substructure, all these sort of chunks and streams of stars surrounding Andromeda. And these are sort of the ongoing accretion events. These are things being ripped apart right now, and their stars are being added to Andromeda. The other thing we want to do is measure the speeds of those stars. So we needed to do spectroscopy. So we had to, analyze the light. And to do that, we had to go to bigger telescopes. And there we used the 10-meter Keck telescope and the 8-meter Gemini telescope to get the spectra of individual stars and measure their speeds from the Doppler shift. So we then can build up this picture of where these stars are and how fast they are moving. And from that, we could start to piece together what kind of feeding habits Andromeda's had.
So is a lot of this kind of using computers to almost rewind, kind of take the current situation and rewind and work out what's happened?
That's what we're trying to do. The problem is that we don't have all the information, right? So we have the velocity along the line of sight towards Andromeda, but not in the plane of the sky. So Andromeda's too far away to get proper motions. So we only have a limited amount of velocity information, and it's very hard to actually get the full three-dimensional spatial structure of the stars. So we're working from a sort of limited data sense, but this is what we now want to do, is trying to piece together the overall dynamical history of that stuff. And we do that, as you said, we do computer simulations. We can put in the effects of gravity and try and rebuild up the accretion to understand, what has Andromeda been doing for 10 billion years?
Yeah, because if you have these kind of remnants of galaxies that have been eaten by the Andromeda Galaxy, how do you know that they are remnants of galaxies? Couldn't they just be kind of star clusters that have wandered close?
So I said we can count the individual stars. So we know when we see a stream or a chunk of stars, we can count up the number of giant stars, and that tells us essentially how many stars there are in total. And so the masses of these things are much bigger than just typical star clusters. So for a dwarf galaxy, this is what we think fell in to be accreted, or many of these things. We are now getting into the very low numbers of billions of stars. So they're bigger than star clusters. They're definitely dwarf galaxies. And we can also tell from the chemistry of these objects. The chemistry tells you something about the size of the gravitational potential in which these things exist. And so, again, this points to the fact that these are dwarf galaxies that fell in and brought in billions of stars at a time.
Do you think that there might then be other galaxies that have been eaten that you haven't yet discovered yet?
So we know that there probably are more ancient accretions. This is how we are able to date some of this stuff. The ancient ones that fell in, they've been orbiting so many times, they've been completely disrupted and their stars are very smoothly spread out. And what we're seeing now are only the more recent ones. But also around Andromeda, we see there are roughly 30 other intact dwarf galaxies, and they're potentially food for the future. So, this notion of galaxy evolution, it hasn't ended. It's an ongoing thing. So I said we want to chart out what has happened to now and also what's going to happen into the future.
When I was reading about this study, there was a really interesting aspect of it that I couldn't quite wrap my head around, and it was this notion of the plane of satellites, and it was the fact that the direction or the orientation of those smaller galaxies could tell you something a bit strange about the cosmic web.
Yeah, so as with all research, right, you do all this research to answer questions and you end up with more questions than you get answers in the end. So back in 2014, this was part of our study as well. I said we discovered these 30-odd dwarf galaxies orbiting Andromeda. We measured their positions, their distances, and their speeds, and what we found is roughly half of them are orbiting in a very coherent sense. They're in a very flat plane, all orbiting around Andromeda in the same way. And this is somewhat mysterious because you might expect that dwarf galaxies could rain in from any direction, so they should be sort of buzzing around like a swarm of bees. But what we're seeing is this ordered motion as these things move around. And so the question is where did this ordered motion come from? And what we some ideas that we have is that we know that material is fed into large galaxies from this thing called the cosmic web, where we have these dense knots of galaxies and clusters separated by voids and sheets and filaments. And so maybe it comes from the fact that material has been fed down the cosmic web and into the Andromeda, and also the Milky Way has a similar structure in a very precise way to give you this very planar structure of dwarf galaxies. But not everybody's convinced that that's the answer. Some people think that this is a sign that we've got something else radically wrong, and there's a small but vocal group that thinks that this is a sign that we actually have our notions of gravity wrong, that something like this plane of satellites forms when you have a collision between two big galaxies, and the only way you can make it work is by not having standard gravity as we understand it. So this is this notion of modified Newtonian dynamics, or MOND as it's called. So some people say that this small-scale weirdness in the universe is telling us something more fundamental about the universe. We don't really know if that's the case yet.
I think most people a lot of people anyway would kind of jump to this conclusion whenever there's something a bit odd going on. But could it in any way be related to dark matter or dark energy or anything like that?
The answer is yes, of course. I mean, dark matter and dark energy are both somewhat slippery topics in that we have observational evidence that those things are there, but we have very little evidence of what they are. And so, dark matter, while we know it has mass, we don't really know how it's distributed. We don't really know how it interacts. And again, it might be that there has been claims that a particular kind of dark matter can form these planes and possibly have dwarf galaxies in these planes as well. But again, anything goes at the moment because we don't have the observational evidence to say that it's this or that. So open question.
I think it's really interesting you were talking about the cosmic web, because I've seen like an artist's illustration of the cosmic web, and to me it looks like a fishing net or something, just kind of like visible matter and then just these massive patches of blackness. Is that actually the way people think the universe is constructed?
Yes, and so I think of it more like a sponge than a web. I mean, cosmic web is the name, but one of the beautiful things is that one area of research I'm involved in is generating synthetic universes. We build universes on computers, so we look at the evolution of matter in the universe over the 14 billion years since the Big Bang, and you start off with the matter being effectively smooth, and you just let gravity do its thing. And what you get is that regions of the universe which are slightly overdense, they start attracting matter from the regions of the universe which are slightly underdense. And this sort of cosmic web naturally forms out of this structure. And in fact, it's somewhat terrifying how well it actually matches, right? And the ingredients are only matter, gravity, and cosmic expansion.
Would such a program like that be able to tell you whether or not there had been habitable planets forming, and then extend that to say there may have been extraterrestrial life on this kind of planet, and you could then kind of infer from that whether or not we are alone in the universe or anything like that? Is that the kind of thing that you could discover? I'm actually writing a grant on this very topic at the moment.
It's a difficult question because of resolution. Our computer simulations, where we simulate the universe, has a finite size down to which we sort of think we're getting the calculations right. And that question of planets, etc., and even stars occurs on a much smaller scale than our simulations. But to study that, you need to put all of those ingredients in. If you want to understand how a planet forms around a star, you've got to know how that star's formed from the gas and how that gas got there, and that gas got there because of the dark matter. So it's all intertwined from the scale of an individual planet up to the cosmic scale. And so we spend a lot of time trying to pin the results between these scales to try and make sure we understand how this on the big scale affects this on the small scale. It's not completely answered yet. And from my research, what I would like to do is try and redo this kind of experiment in other universes where we mess around and change the laws of physics to see if habitable planets are common or rarer in different kinds of universe. So it's still an open question, but I think it's a really interesting one.
But if you were to change the laws of physics, would that not create an unrealistic scenario?
Well, it creates an unrealistic scenario for our universe, right? But there is this notion of the multiverse. Okay, so it leads to pub fights. Does the multiverse? It's this notion that our universe could be just one of an almost infinite number of other universes out there somewhere, and that each of these other universes has been essentially imprinted with its own laws of physics. So the laws of physics in some other universe is different to the laws of physics that we have in our universe. And one of the questions that I'm very keen to answer is what's the impact of changing those laws of physics? I mean, is the formation of stars and planets just a generic thing that happens in any old universe with any old physics? And what we already know is that doesn't seem to be the case. If you stray a little bit away from the laws of physics that we have, i.e. you make gravity a bit stronger, you change the strength of the electromagnetic force, you rapidly end up killing the potential for life in the universe. So this is this thing called cosmological fine-tuning. Why do the laws of physics in the universe that we have seem to be just right for us to be here? And as I said, it leads to pub fights a lot of the time when people get to discuss this.
Does the view of the multiverse come from the notion of an infinite universe? In other words, if the universe is infinite, anything's possible?
That's one version of the multiverse. I should lay the cards on the table. The multiverse is not a single idea. It's a group of ideas, and nobody's quite sure if all the pieces are part of the final answer. There is one version of the multiverse, which is that there's just our universe, but physics is different over there compared to here. But over there is so far away that we would never have contact with it. And so if you've got an infinite universe, you can fill it full of infinite patches of over there's with different kinds of physics. There's another notion of the multiverse where the universes are actually individual universes in a higher dimensional multiverse. Again, we don't know which is the right kind of picture, and we don't even really know how to test those pictures, but I think it's pretty cool to think about them.
Definitely. There was actually one aspect of your Andromeda paper that I wanted to just come back to, because I really wanted to kind of talk to you about it, and it was basically this idea that the Andromeda Galaxy is eventually going to consume our own galaxy, the Milky Way, isn't it?
Consume is possibly not the right word,
okay.
but so what's happening is that Andromeda and the Milky Way are hurtling towards each other. And then in roughly about 3.5 to 4 billion years, they're going to collide. So over most of their history, right, the Milky Way and Andromeda are very similar-sized galaxies, and they've been consuming smaller galaxies, and because it's not a Hollywood script, right, in galaxies, the big guy always wins, right? Mm-hmm. The little galaxies get torn apart. when Andromeda and the Milky Way meet, because they're roughly equal size, they're going to end up totally disrupting each other. So they're going to approach each other. The gravitational attraction is going to rip apart the beautiful spiral disks that define these galaxies. And eventually, all the stars will be either thrown out into intergalactic space or merge back together into a really sort of boring-looking elliptical galaxy. I mean, it would be great to be around to see that collision because, you would see Andromeda getting larger on the sky. It would become very, very visible. Then you would see the spiral arms sort of warp and distort. Then gas clouds in the galaxies would collide and you'd get this new burst of star formation, so the sky would light up like a Christmas tree. Gas would get funneled down into the black holes at the centers of the galaxies due to the disruption, so the centers of the galaxies would light up as well. So this would go on for a few billion years, but after that, then everything would settle down and we'd be left over with this rather amorphous blob, which is, I hate to, it's called Milkomeda. I really hate that name, but it's the leftover remnants of the collision between the two big galaxies.
Oh, I just got it because it's the merging of the two names.
Yeah.
I just got that.
Yeah.
But like, would Earth survive? Like, if we were still alive, what would actually happen to us?
So there's a couple of things you have to think about. So firstly, when you have two big galaxies or galaxies of any size colliding, it's an amazing fact that stars themselves are actually tiny compared to the distances between stars. So in a collision between galaxies, the chances of one star hitting another star are almost zero. So the stars will just sail past each other, and they will probably hold on to most of their planets, right, other than the stuff in the outermost regions of like the solar system. So yes, the Earth could survive that kind of collision, but the big problem we have is that we're now talking of timescales 4, 5, 6 billion years, and we know that the Sun is roughly, already 5 billion years old and is halfway through its lifespan. And over the next 3, 4, 5 billion years, the Sun is going to stop in a nice sort of G-type dwarf that it is today and start expanding into its red giant phase. And on these long timescales, the Sun will have expanded so much that it will have swallowed Mercury, Venus, Earth, and then possibly Mars as well before the Sun enters it, at the late stages of its evolution. So if we want to see it, we should move over to a younger star, and I think the view would be rather spectacular. But on that timescale, it's at the end of the solar system and the Sun.
Right.
Sorry, there's no happy endings in astronomy. You know this, right?
Yeah, definitely food for thought, though, isn't it? We put a shout out on our social media channels, saying that we were going to be speaking to you. And got people to send in their questions. So I was wondering if you'd be up for answering a few questions.
Let's give it a go.
So John Wells on Facebook said, is the universe infinite? And if so, how could an infinite universe have begun from a finite point? According to if the Big Bang Theory is correct and it started from a single point, how could a single finite point have grown into something infinite?
Because of sloppy language. Okay, so let's go back to our universe as we understand it. And most of the 20th century was spent trying to work out the geometry of the universe. Is our universe a closed universe with a finite volume, or an infinite universe with an infinite amount of space? And what we think we've found is that our universe appears to be an infinite universe. I.e., if you head off in any direction, there's an infinite amount of universe out there. So the question is then, of course, we always hear about this time when the universe was the size of a grapefruit. And the sloppiness comes from the fact that what they're talking about there is the observable universe. So that's the sort of patch of the universe that could be reached by a light beam traveling since the Big Bang. And so what we have is that in the early times, that patch was very, very small. And today, that patch is now 90-something billion light years across. But that patch of observable universe is still inside an overall infinite universe. So if our universe is infinite today, it's always been infinite, right? It's been spatially infinite. It was today, yesterday, 5 seconds before the Big Bang. And at the Big Bang itself, the universe itself was spatially infinite. Okay. But weird things happen at the Big Bang that would take too long to sort of go into. But yeah, if I said, as far as we can tell, the universe is infinite. And that means that there's infinite space beyond our observable universe. But when we talk about the size of the universe, we're often talking about just that observable patch that we had contact with due to the speed of light.
I think that kind of brings us on to another good question by Steve Green on Facebook, because his question is, what is space? And I suppose he potentially means, if all that observable matter was the size of a grape, what was beyond that? What actually is space? Is that even answerable?
What is space? So 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 there's one of my favorite questions is, what is time, right? Time is the thing that stops all events happening at once.
Okay.
Space is the thing that stops all events happening in the same location. I mean, that's as far as we can say that is what space is. It's the thing that separates events. But if you want to talk about space as what is it, there is no real answer that will ever satisfy you. We don't have any equations that space is this or it's made of that. There are ideas that space could be some kind of quantum weirdness on the small scale, but very hand-wavy ideas. So the what is space is a somewhat an unanswerable question. At least I can't think of a satisfying answer of what is space. But we understand how material behaves in space, right? So this is what Einstein's special and general theories of relativity tells us, is the relationship between how things move around and how time travels and how time changes and how things move in relation to each other. We can write all that down, but nowhere in there do we have to say, and space is this for this to happen.
Okay.
Actually, as a recommendation, there's a beautiful YouTube video where Richard Feynman's trying to explain to somebody what is a magnetic field. And he eventually says, well, there's no answer that's ever going to satisfy you, because you want me to say that it's something along the lines of something you understand, like a rubber band or something. But it's not. And at the end of the day, you get to say, this is what it is. It's its properties. So you should check it out on YouTube. It's very good.
Nice. Good tip. And Yogesh Bang on Twitter asked, this is quite a complicated one, so maybe I might get it wrong, but he says, does the Hubble constant affect the frequency of gravitational waves traveling in the universe? How can we determine the distance of the origin of a gravitational wave if the universe is expanding?
The answer is yes, but you have to be very careful about what you mean. So we know that when light rays travel to the universe, it looks like their wavelength expands. This is the cosmological redshift. But in reality, it's slightly more complicated than that. It's not just space grabbing hold of a photon of light and stretching it. There's a more complicated thing in relation to the observers and what happens to the universe in between the photon being emitted and being detected. And it's similar with gravitational waves as well, except gravitational waves are in that space stuff, which a moment ago we couldn't describe, right? But it does appear that there is a similar kind of effect that happens for gravitational waves traveling through the universe. They look like they would be redshifted in the same kind of way that a photon would be. But again, it's slightly messy because we're now talking about something moving in the background of the universe rather than something moving through the background of the universe. And what was the second part of the question? How do we know?
How can we determine the distance of a gravitational wave if the universe is expanding?
Because let's do it with the light example, because we can always do the analogy back. So when a light ray travels across the universe, right? We know that it gets redshifted, etc., and we can detect that at our telescope. And what we know is that our observation of that distant object has been distorted by the expansion of the universe. So how bright that object appears is different because the universe is expanded to how bright it would have appeared if the universe wasn't expanding. We can actually do exactly the same kind of thing with gravitational waves. Gravitational waves come from particular kinds of sources, be it merging black holes or neutron star collisions. And so essentially what they give us is the expected kind of signatures we should see. And when we compare that to what we see in our telescopes, we have an idea of how far this must have traveled by how bright or faint that signature looks in comparison to what we've been able to calculate from the mathematics.
It's quite impressive science, considering how relatively young gravitational wave science is. I mean,
you have to be very careful. So, sorry, I didn't mean to interrupt there, but I mean I can. So
in terms of the first actual confirmed detection,
that's right. Yeah. So the great benefit of gravitational wave astronomy is that gravitational waves were so difficult to detect that it meant there were like 40 to 50 years of theorists sitting around basically going, what are we going to do? So they basically sat there and they calculated all of the potential signatures that we would see. So they said, right, if we imagine we had two black holes merging, what kind of signatures. And often you need supercomputers to do this kind of thing. So they essentially made a catalogue of all the kinds of signatures we would get from the universe. So I got up in the middle of the night, Australian time, to watch the announcement of the gravitational wave discovery. And there's only two things that I'll watch in the middle of the night: international rugby and the announcement of gravitational waves. And they put up the signature that they got from LIGO, and I looked at it and just went, yeah, that's it, because I'd seen so many predictions from theories going back 20, 30 years that this is what we should expect to see. And this was exactly that was seen. So the fact that they were so hard to discover meant that the theorists had a lot of time on their hands to calculate all these things.
Okay. Well, while you're here in the UK, I understand you're going to be talking about the habitability in the universe.
Yes.
Yeah, and I was wondering if you'd what's your kind of stance on the prospect of life somewhere else in the universe?
So, look, like a lot of people, I started off, being a sci-fi fan and being an optimist with regards to the potential of intelligent life in the universe. Of course, that's what we want, right? I mean, we want to know, are there civilizations out there? But looking at this from a scientific point of view, I've come down on the side that we are potentially the only intelligent life, at least in this galaxy. If there is other life out there, it's either very primitive life, pond scum, slime, that kind of thing, and that advanced and especially intelligent life, and especially intelligent life that could colonize the galaxy, is vanishingly rare. So we have got no observational evidence that there's any kind of intelligence out there, and limited evidence that there's intelligent life on this planet as well, right? So, but yeah, so to me, it looks like the observations are telling us that we are probably alone in the universe.
I think whenever you kind of look at how close we are to discovering something within our own solar system, or at least just that we have discovered conditions where life could arise, say like on Enceladus or something like that, that kind of gives me hope and kind of thinks, well, if we're that close in our solar system, surely somewhere out there, there's a civilization exploring their own solar system.
Maybe that it's. We do not know how life started, right? And so you could have the conditions for life throughout the universe, and it may have only happened here, right? We just do not know what that spark was. And there's a lot of argument about, is that spark a generic thing, or is it, as I said, is it a one-off event that was only recreated here on Earth? And it's kind of, I've been speaking to some astrobiologists about this. You actually need some interesting conditions. If you look at the Earth, one of the weird things is that we are 70% water and 30% land. And if you look at the expectations for planets out there in the universe, you'd expect either they are completely water worlds with kilometers and kilometers of water and no land, or they're dry. And it's very rare to get something in between. And what my biologist friends tell me is that we probably needed something like tidal pools to give us the right conditions where you have drying and wetting cycles that give us the initial kind of structures that led to life on this planet. So already you can start, there's this rare Earth hypothesis that Earth has a lot of interesting features that are not probably shared throughout all of the planets in the galaxy. And, we should be very careful about just saying, well, life is here, therefore it must be everywhere. And I said, people have looked for it. People have looked for the signatures of civilizations. We should see them, right? Because the cheapest, most abundant source of energy in our galaxy is starlight. And to use that starlight, you've got to capture that starlight and process it. And it comes out at lower energies. It comes out as infrared. But we still see plenty of starlight. So if there's a civilization out there that's not using starlight, then what are they doing? It's the cheapest source of energy that there can be. So, and we see no signatures of them doing it. So
I suppose the problem could be that life did exist at some point in the distant past, but it's the blink of an eye, isn't it? So
that's right. And
it's been and gone.
There is this notion called the Great Filter that maybe intelligent life does come along every so often, but there is some barrier it hits. And that barrier, it might be it destroys itself through war, or it destroys itself through climate change, or whatever. That something happens. And, the philosophers are now wondering, is the great filter behind us, have we stepped beyond that point? Or is it still something in front of us that we should be worried about? But it could be that, in any sort of intelligent life, before it gets the ability to get off its planet and to surrounding stars, essentially wipes itself out. So there might be archaeological remains scattered through the galaxies of the almost rans. But that's not what we're interested in, is it? Don't we all want sort of Star Trek civilizations out there, rather than just there being Indiana Jones ruins now and again scattered on the loneliest of planets?
I think so, and obviously that's what kind of the Voyager and the Pioneer things were. The inscriptions and all that was kind of hoping to discover something else that would be able to learn about our culture and kind of want to visit, perhaps. That's
right. And of course, there were people very upset that we were sending out the fact that we're here on this planet. Please come and visit us, because you don't know what the attitudes of anything out there could be. But as I said, I don't think we've got much to worry about. I don't think anybody's going to be looking at the plaques on Voyager and Pioneer anytime soon.
Well, on that note, I think we'll leave it there, Geraint. Thanks very much for coming into the studio today and speaking to us.
Thank you very much. It was great.